Hey everybody, Mr. Bowman here. This is another video on 3.13 probability concepts. In particular, we're focusing on the 4 merit questions for the 2020 exam. Before I get into it, just a reminder, all of these questions are written by the NZQA, so they're the actual exam questions from previous years. And I've compiled and put all of them in one place, so have a look at the link in the description if you want to kind of see more of these practice exam questions. So let's get into question number 5 first. So after exercise, we've got some blood sugar and the dehydration levels of 80 Year 13 questions or Year 13 students from one school were measured. Straight away, because there's 2 variables, I'm thinking, is it going to be a two-way table? Is it going to be a tree with the blood sugar and then the dehydration afterwards? So we're going to keep an eye out for, but that's what I'm thinking so far, table or tree. They were classified as, so the blood sugar people were classified as low blood sugar or normal blood sugar. So that kind of seems like 2 outcomes. That could be, one side of a two-way table. That could be 2 outcomes over there maybe. And the dehydration levels were classified as dehydrated or not dehydrated. Of the 23 students with low blood sugar, 20 of them were also dehydrated. And then we've got 53 students in total were not dehydrated. So at the moment, I'm thinking it's probably going to be a two-way table. The main reason being is I'm not given any probabilities for my probability tree, so I think maybe a table is going to be more appropriate. So explain whether students being dehydrated and a student having low blood sugar are mutually exclusive. Gosh, so a bit to compact to this question. So let's start off by making the statement. So if they are mutually exclusive, the probability of being dehydrated and the probability of having low blood sugar should be equal to 0. So let's start off by making that statement. So if D, standing for dehydrated, and low blood sugar, we'll call that LBS, are mutually exclusive, then, and this is where it's going to get a bit mathy, we know the probability of dehydrated and low blood sugar must be equal to 0, because if they're mutually exclusive, it means they shouldn't be able to happen at the exact same time. It's impossible for them to happen. So I'm assuming we're going to have to calculate this probability with all the information we're given, perhaps using a two-way table. So let's construct that two-way table. So down this side over here, I'm going to write dehydrated and not dehydrated. And along the top there, I'm going to write low blood sugar and then not low blood sugar. So that apostrophe meaning the not. So I've got what my table looks like. Let's now start infilling. So I was told there are 80 students in total. So that 80 is up there. So that's going to be the grand total down the bottom. Looking through the questions. So we've got of the 32 students with low blood sugar. So my low blood sugar group is going to be 32. So that's going to be 32 over here. That means I can figure this number out here. And that's going to be 48, which was the 80 minus the 32 to give us the remaining 48. So 48 people don't have low blood sugar. So I've now used, I've used the 80 up there, and I've used the 32 here. Of these 32, 20 of them were dehydrated. So that means of the low blood sugar group, this 20 up here, we're going to be dehydrated. So that's 20, which means we can figure this one out here to be 12. So 32 minus 20 gets me to that 12. And then finally it says the only other number we've got, hopefully it's enough to finish the table, 53 students in total were dehydrated. So this dehydrated column or row up here has got to be 53. And it does look like we should be able to finish it up here. So this number down the middle here is going to be the 50 minus, sorry, not the 50, the 80 minus the 57. And I'm doing the math in my head, but hopefully you're getting 27 as well. This kind of number in the middle here is going to be the 53 minus the 20, which gets me to 33. And then finally, this number here, I could calculate it going this way or this way. Both are going to get, or both should get you to the same answer. But that number there, 50 minus 12 is going to get me to 15. And just checking, 35 plus 15 does get me to 48. So I haven't got any math errors anywhere along my table. So based on this table, so don't forget, we're looking at being dehydrated and having low blood sugar. That's going to be this group up here, isn't it? So there's 20 students out of the 80 who have low blood sugar and dehydrated. So Let's find the probability of that based on my table. So the probability of someone being dehydrated and having low blood sugar is equal to 20 over 80, which is equal to 0.25. And remember before I said if it's equal to 0, I've shown it's mutually exclusive. Because I've got a number that's not 0, I've showed the events are not mutually exclusive. So that means the events, it is possible for them to happen at the same time. So that's going to be my little statement here at the end. So as a result, the probability of being dehydrated and having low blood sugar is not equal to 0. And then we go therefore. So let's finish up by wrapping up our conclusion. Therefore, being dehydrated and having low blood sugar are not mutually exclusive events. So quite a bit to unpack for this question, but hopefully it makes sense. Key thing to note, during this write-up, I've written D and LBS. I have been a bit lazy. I probably could have written that out fully. Maybe in the exam, make sure you do that. So we are now on to question number 6. Carrying on with the dehydration and the blood sugar theme from the previous question, but we actually didn't need any of that information. So both dehydration and low blood sugars are thought to decrease cognitive thinking or cognitive ability. So it's kind of another variable that they're throwing in there. So in a separate study involving a different group of year 13 students, it was observed that for the 15% of students who were dehydrated and who had low blood sugar, so that's having both, 45% of them had decreased cognitive ability. For the 57% of students who were not dehydrated and had normal blood sugar, so not dehydrated and not low blood sugar, 5% of them showed decreased cognitive ability. And then for all other students, 32% of them had decreased cognitive ability. Okay. And then the questions asked us to calculate the probability that a randomly selected student showed decreased probability. So because we've now got kind of probabilities, I'm thinking it's going to be a probability tree based on the classification of the students, if they have diabetes, so not diabetes, if they've got dehydration or low blood sugar, etc. So this one was a bit tricky. So the first group of people, they could have been the people who are dehydrated and with low blood sugar, right? And then the second group of people could have been people not dehydrated and not low blood sugar. That was the two groups decided or described kind of in this section of the question. And it said generically at the bottom for other students. So that might be people with one of these, but not necessarily both of them. So what I'm going to do here, I'm just going to write other as that third group over there. So it said 15% of students were dehydrated and had low blood sugar levels. So that means this group up here is going to be 0.15. It said 57% of students had neither of these. So that group up here is going to be 0.57. And then finally, the remaining group must have had one of them, but not necessarily both of them. And when I did that math earlier, I got 0.28 in relation to this group here. So we're now going to split this off. So we've broken up their dehydration and blood sugar combinations. And now we've then got to figure out, are they going to have a decreased cognitive thinking or are they not going to have decreased cognitive thinking? So each group, I'm going to call DC for decreased cognitive ability. And then this is going to be not decreased, or basically stayed the same, or maybe even increased. So we've got decreased cognitive ability, and then we've got not decreased. And then finally down the bottom, decreased cognitive ability, and then not decreased. So I now need to figure out, based on the previous outcome, what these ones here are going to be. And the question has all that information for us. So starting off with my first bullet point, of the 15% of students who had dehydration and low blood sugars, 45% of them had decreased cognitive ability. So that means this top branch here is going to be 0.45, and that means the remaining 0.55 did not have a decrease in their cognitive ability. For the second group, 57% of the students who were not dehydrated and had normal blood sugars showed 5%. So that's going to be this group, so not dehydrated and not low blood sugar. And 5% of them had decreased cognitive ability. So that's going to be 0.05 up there, which means not decreased cognitive ability is 0.95. And down the bottom, it said of the other students, 32% of them had decreased cognitive ability. So this decreased cognitive ability up there, that's going to be 0.32. So this question is pretty messy in terms of the tree. That means that bottom there, I think that's 0.68 for not decreased cognitive ability. Okay, so I've done my tree. Back to the question. It's asked us to find the probability that someone's got decreased cognitive ability. So we're trying to find the probability of DC or decreased cognitive ability. And you're thinking of the tree, you've got 6 different outcomes along the tree there. Which of them relates to someone with decreased cognitive ability? So it would relate it to this branch up here. So we need that branch, not this branch up here, because the D dash means it didn't decrease. This branch is all good, not this branch over here, because they didn't decrease. And then finally, this branch is all good, but we don't care about this branch here. So we've got these 3 ticks. So these 3 branches are the branches that are going to be relevant to the question. We now need to add all of these up. So the first branch would have been 0.15 times 0.45. So it's going to be the first bit of my calculation. So 0.15 times 0.45. We're then going to add on the second branch, 0.57 times 0.05. So it's going to be plus 0.57 times 0.05. And then finally, this third branch here, 0.28 times 0.32. So 0.28 times 0.32. Oh, I've written an equal sign there, but that should be a plus sign, shouldn't it? Finally, we're going to plug that into our calculator. When I did this earlier, I got 0.1856. Okay, we are now on to question number 7. And I really love seeing questions that look like this. Do you see how it's got this huge list of bullet points? So straight away, the huge list of bullet points, I'm not saying it's guaranteed, but 95% of the time, this is going to be a 3-way table or a 3-way Venn diagram. So as we're reading through the question, let's keep an eye out for the 3 variables, just to confirm that. And then let's start, I'm assuming we're going to start drawing one of those. So we've got a medical clinic, interested in understanding the probability of a patient being diagnosed with heart disease, diabetes, or stroke. Straight away, I've got my 3 variables, right? You either got a heart disease or you don't. You either have diabetes or you don't, or you've had a stroke and you haven't had one. So that's almost guaranteed already. So we've analyzed 5,000 patients in total, and they found all of these here. So we're going to get into that once we start constructing our table. And then the question has actually asked us, calculate the proportion of the patients that were diagnosed with a heart disease, but not a stroke or not diabetes. So that question is going to be a bit annoying. So just breaking that down, we're trying to find the probability they have a heart disease and they don't have diabetes, that's why it's D dash, and they didn't have a stroke, and that's why it's S dash. So that's the probability we're trying to find out. So let's sketch our graph or our 2-way table, and I'll try to draw a bit bigger. I appreciate last time I did one of these in a video, I did kind of smush it up together and there wasn't the best room for working. So there are my 3 horizontal lines, and going down the side here, the first variable mentioned was heart. So group number 1, it's the people with the heart disease or the people without the heart disease. And variable number 2, I make up another one here and then I chop it in half. That's variable number 2. That relates to people with diabetes. I just do them in the order they come up in the question. So that there will be D for diabetes and then not diabetes, D for diabetes and then not diabetes. And then finally, the next group of people were the people who have had a stroke. They're going to be my variables kind of heading down here. So people who had a stroke and then people who did not have a stroke. And we're just going to carry on this line here to get the diabetes people sorted. There we go. So I've drawn my table. Hopefully you can see how I've set it up. They're a bit messy to draw. Often it is worth practicing it to make sure you're happy with it. And let's go through all the numbers. One by one, let's put the numbers into place. So the first number in the question said 5,000 patients. That's the grand total. So we know there were 5,000 patients in total as part of the study. So let's cross off that. 71 people were diagnosed with a heart disease, with diabetes, and with a stroke. So that's 71 had all of them. So that they're related to H and D and S. So that's going to be H, D, and S. So that's going to be kind of this box up here. So that there was 71. So I'm going to put a big tick there because I've used that information. 1,359 were not diagnosed with any of these conditions. So that's going to be H dash and D dash and S dash. So H dash, D dash, S dash. So that's going to be kind of this bottom box over here. So they've got none of these conditions. So I guess they're the healthiest ones of the bunch. So 1,359. So I've used that information. 1,907 had a heart disease. So that there is just the H total. So it's going to be over here. So we've got 1,907. This number is really nice because we can now figure out the people who didn't have a heart disease. So if I go 5,000 minus 1,907, I'm going to get 3,097 people without the heart disease. So I've now used that information there. So 1,814 had diabetes. So because diabetes is my second variable kind of tucked in there, then these ones normally are a bit more awkward. So the diabetes people are going to be these two groups plus these two groups here. So I don't really have enough information to do anything with that number yet. So what I'm going to do here is I'm going to do a bit of coding. So I'm going to put a little plus sign in each of those four boxes. So there's a plus sign there, plus sign there, plus sign there, and plus sign there. And I know all the plus signs, so I'm going to put a little plus signs here, all the plus signs need to add to 1,814. So let's put that at the top there maybe. So plus sign is equal to 1,814. So I'm going to have to come back to that. So when I've got 3 of these 4 boxes, I can then figure out the 4th one, but can't do it at this stage. So tick, I've used this, I've had to code it. 627 were diagnosed with a stroke. So this is the stroke group here. So that's a nice one to have the total for. So that means the bottom number here is going to be, I wrote 6,000, I meant 627. I can, like that, I can use subtraction from the 5,000 to figure out that number there. So that number is 4,373 people didn't have a stroke. So I've used this number now. Okay, 388 of those diagnosed with a heart disease also had diabetes. So heart disease and diabetes relates to these two groups here, right? So it doesn't say if they had a stroke or not, so that's why it's both groups. And we have one of these, which means we can figure out this group here. So this group is going to be the 388 minus the 71, which gets me to 317. So I was able to deal with that. And then finally, 170 people diagnosed with a heart disease were also diagnosed with a stroke. So heart disease and stroke would be these two groups here, right? Heart disease and stroke. And we know 170 of them. So I'm going to use 170 minus 71 to get me this number in the middle, and that's going to be 99. So I've now done everything I can. The only bit of information I haven't fully used here is that plus sign, 1,814. And that's because I'm still, of these plus signs, I'm still missing one of them. I need one more to then be able to figure out the last one. So we're going to need to do a bit more mahi to get that. So the first thing I've spotted is I can figure out this group up here because all 4 of these needed to add to 1,907. So what I'm going to do is I'm going to go 1,907. I'm going to subtract these other 3 numbers. And that's going to get me to this group here in the middle. And when I did that math, I'm getting 1,420. Now, this number is really nice. Now, if you're looking at the not stroke people, I'm only missing this one number in the middle, which means, again, I can use subtraction to work that out. So I'm going to go 4,373. I'm going to go minus this, minus this, minus this. And that's going to give me this leftover number in the middle, which I get to be 1,277. And this is perfect. So back to my plus signs. Do you see I've got 3 of the 4 now? I'm now going to use subtraction again to get the missing one over here. So my 814 up the top minus the 3 plus signs is going to give me that leftover plus sign there. And I get that to be 149. And then finally, I can work out the stroke group that's missing down the bottom there by doing 627 minus my other 3 numbers. That gets me 308. So I've now got my table, so it was pretty messy to get here at this stage. I can now actually get back to answering the question. Reminder, I was asked about the probability of having heart disease, but not a stroke and not diabetes. So we got heart disease, not diabetes, and not stroke. So that's going to be this number over here, 1,420. And don't forget, that's out of the 5,000 people in total. So the probability of having heart disease, not a stroke, and not a diabetes, sorry, I keep saying those the wrong way around, but writing them differently, is going to be equal to 1,420 divided by 5,000. That's a fraction. Plug it into your calculator as division, and hopefully you're getting 0.284. And that was the exact number, so I didn't need to deal with any rounding there. Okay, we are now on to question 7b, and sorry that this one's called 7b. When I originally kind of put all these questions in a Word doc, I forgot about this one and kind of shoved it back in after the fact. So we've got a count of 250 students, and it summarizes whether or not they have ear piercings or not. And you kind of see it's split on male and whether or not they have a piercing. So male, female, piercing, no piercing. So explain whether a student is female and a student has ear piercing, explain whether they are independent. So this is something that comes up really, really common, this kind of independent type question. And the formula I want you to remember, if events are independent, so the probability of event A will be equal to the probability of A given B. So what this is saying is, so A and B are the two variables we're comparing. So, but this is basically saying, you know, the probability of A will be the same as the probability of A given B. So that means B should not impact A, which means it should just be the impact, or that should just be the probability of A in the first place. So this type of formula you should remember off by heart and know exactly how to do this type of question. So let's get into it here. So our variables here are if they are female and if they have a piercing. So we're going to use P and F as our one. So we're trying to find, so if if F and P are independent, then the probability of the probability of P, so the probability of having a piercing should be the same as the probability of having a piercing given they were a female. So the fact that they're a female shouldn't have done anything, right? Because the question's kind of trying to tell you that, it shouldn't impact it because they're independent of each other. So let's go ahead and calculate these probabilities. So the probability of getting a piercing, so that's this group over here, that's going to be those two added together divided by the 250 total. So that's going to be 58 plus 91 over the 250 students. So when I did that math, I got 0.596, and that was not needed for rounding. I'm now going to find the probability of someone having a piercing given they were female. So this is a conditional question, so we only care about the females of this group. So let's make that our denominator. So the total number of females in this group was 91 plus 47. So these are the females of the group, and of these who had the piercings, it was 91 of them. And when you plug that into your calculator, you should get 0.6594, and that one there was rounded, unlike the previous one, rounded that to 4dp. So we can see these numbers here, they are not the same, which means the fact that the person investigated was a female had an impact on whether or not they had a piercing. And for me, that kind of makes sense because I think a lot of guys don't get their ears pierced, and females tend to do that a lot more. So maybe it makes sense that females are more likely to get a piercing. So based on that, we're now just going to state our conclusion. So as the probability of having a piercing is not equal to the probability of having a piercing given they were a female, we know that events F and P, so that's basically their gender and whether or not they had a piercing, are not, I'm going to put that in caps, not independent of each other. So not independent of each other. So that means, whether or not you're a female does have an impact on the probability that you have a piercing. So I'm just going to explain that in a bit more detail. So that is a person's gender may influence the likelihood of them getting a piercing. The likelihood of them getting a piercing. There you go. How do I spell piercing? Forgive me, I'm not the best speller in the world. That's why I'm a maths teacher, not an English teacher. There you go, piercing. So that wraps up the fourth and final merit question from the 2020 exam. Hopefully you found them useful. If you're not sure on any of these, don't hesitate in reaching out in the comments or whatever it might be. Ask for help and I'll try to reply with something that's useful for you.